Okay, so we are in an introduction to statistical learning. We are in chapter 4, and this video is tackling question 14, which is part of the applied problems. I will be doing this in R. I was making videos in Python, but the code is for Python is sufficiently kind of long and a little bit difficult to look at. And so I will just stick to making videos in R, but there is a Colab sheet available for Python, and that should be in the description. All right, so question 14 here is long. It's all of this, and so we won't read them all at once. We'll just kind of go one at a time. But we are going to develop, well, actually several predictive models using different methods. Whether a given car has gas mileage that is well, whether it's high or low, based on a data set that is part of the ISLR2 package called auto. Okay, so before we get into any of the questions here, we need to install and load the ISLR2 package, because again, that contains the data set that is called auto. And I'm going to just rename this data set D, just to reduce my typing. Okay. So part 1 is pretty basic. We're just going to create a binary variable. Actually, let me add just a little bit of code here to just see what D looks like, what our data set looks like. Okay, so we have all of these different variables over here. And you'll notice that one of them is mpg, or miles per gallon. Okay, and what we're going to do, it also has mpg01, but that's because I've already ran the code below, and we're actually going to create this variable. So what is mpg01? Well, we're going to take the median of mpg, and if the gas mileage of a particular variable is below that median, we're going to call it 0. And if it is above the median, we're going to give it a value of 1. Okay, so that's what we're doing in part A. Okay, so the code that I used for this is right here, right? So I have D, and I assigned a new variable to that data set called mpg01, like we're supposed to, and I say if miles per gallon is above the median of miles per gallon, then assign it 1, otherwise give it a 0. Okay, so that's what we have there. All right. I've already ran that, so I won't run it again. Okay, so now for part B, we're meant to use some graphs to explore the relationships between a bunch of these variables with mpg01. Okay, so I'm going to make graphs for, I think, most of them. I won't make a graph for mpg because, well, it's basically deterministic of mpg01. Okay. But this is the code that I use for it, so I'm going to have a 3x3 display, and you can kind of march through this code a little bit, but basically I'm going through each variable in D, but if that variable is mpg01, I skip it, and then if it is one of these variables, and these I'm calling categorical variables, then I'm going to make a box plot. But otherwise, meaning it's a continuous variable, I'm going to make a scatter plot. Okay, so that's all that this is doing. So let's look at all of that. I'm going to open this up in a new image here, or in a new window. Okay, and so this is what we get. So again, you have mpg01. I guess I did make one for mpg, but you can see how clear cut it is. I mean, again, because it's deterministic. But we have the explanatory variable, or what I'm calling the explanatory variable, or potentially explanatory variable, on the x-axis, and then mpg01 on the y-axis. Okay. So for instance, if we go over here to weight of the vehicle, we see that heavier vehicles tend to have an mpg value, or mpg01 value of 0, meaning it's below the median. Okay, and that makes sense. All right. Now as part of this question, what we're supposed to do is to look at the different plots and try to determine which features or which other explanatory variables are likely useful in predicting mpg01. Okay, well, I have a couple things to say about this. Okay, so again, we're not counting MPG as an explanatory variable because it's deterministic of MPG01. But the way that we might do this, like for instance for the continuous variables, is to take, well, it's to look for very clear separation between this upper band and this lower band, right? So weight, and horsepower, and acceleration kind of all seem to be predictive to some extent or another. Displacement, it's a little bit less clear because we have 0 values spread all along, and 1 value is just to one side here. So we might say then that at least these 3 variables are predictive. Maybe displacement is as well. But I actually have an issue with what they're asking us to do here, because these are all two-way relationships: weight with MPG01, acceleration with MPG01. But many of the, well, I think all of the methods that we're going to use to try to predict MPG01 are using conditional relationships. So, for instance, it's not what is the relationship between weight and MPG01, but if we were using all 3 of these variables, or all 4 of these variables, say, right, each of these continuous variables, as predictor variables, then what our models are doing is saying, how much does weight predict MPG01 after we account for each other predictor variable in our equation? And you can't really intuit that. In fact, you probably can't figure it out with these particular plots. But even if you had a more extensive menu of plots, it would be very difficult to try to intuit that. And so to look at these plots and then try to determine which ones are going to be predictive, probably, well, it might not be an optimal solution. Okay, so but I'm just saying that. Okay, so let's go back here. So that's what are we on? Part B. So now, if I go to Part C, we are meant to split the data into training sets and testing sets. So all I'm doing here is I'm determining how much of my data I want to be training data, so training proportion, and I'm going to say 75%. I could call it training percentage or whatever, but 75% of my observations then are going to be training data, and the rest are going to be testing data. That's what I've done here. So how many are being how many samples are in the training set? Well, it's the training proportion times in row times the number of entries in my data set. And because that might come out to a non-integer, I'm rounding up to the nearest whole number. Okay, and then my training index is I'm going to sample train in number of values between 1 and the number of rows, or the number of cases that I have, right? So this will say, if D has 100 total entries and I am supposed to get 75 of them, I will randomly sample numbers 1 through 100, and I will randomly sample 75 numbers between 1 and 100. Okay, and everything that I sample is going to be called a part of the training data, and everything else is going to be called the testing data. Okay, so I've ran these, and then you can kind of see what these look like. So our training data has 294 observations, and our testing data, it's kind of muddled in here, but let's try to find it. Has 98 observations. Okay. All right. Okay. So now we're in Part D, and as part of Part D, what we're going to do is we're going to use linear discriminant analysis on the training data to try to predict MPG01. All right. And the variables that we're supposed to use, again, we're supposed to determine from here. So if you use different variables, so I'm just going to use these numerical variables, okay? But if you use number of cylinders or country of origin or whatever, then you're going to get different results, and that's fine. So anyway, now after we train the model on the test set, we're also supposed to find the test error. So in other words, we're supposed to predict the data that's in our testing set of data. Okay, so we're going to do all that. So to do this, you probably need to install and load the mass package. Okay, and then and then from the mass package, I'm going to use the LDA function. And so I'm just using. So again, I'm trying to predict MPG01 based on these other variables here. And what data am I using? I'm using the training data, dtrain. Okay, and then I want to find the probability of MPG being 0 or 1. And so to do that, I'm going to use predict. What am I predicting? What model am I predicting from? LDA fit, which is what we just ran. But I'm trying to predict this new data. Okay. All right, so my new data is this. And then what type? It's the response. Okay. And then I set a rule. So this is going to give me a bunch of probabilities for the value of MPG01. And then I'm using a rule that says if it's above 50%, if the probability of being 1 is above 50%, then I will just say it's 1. Otherwise, I'll call it 0. Okay? And I'll build a confusion matrix here, and then find the overall test error. Okay, so I run this. I get my confusion matrix here. Okay, so again, when I'm predicting 0 and it's actually 0, I get 35 of those correct in the testing data. When I predict 1 and it's actually 1, I get 58, and sometimes I confuse the two on these kind of non-diagonal terms here. Okay, and so what I'm using for my test error rate is I'm just summing everything in this matrix here. I'm summing these non-diagonal terms, 5, divided by everything in the matrix. Okay, the sum of everything in the matrix, and so we come out to 5%, roughly 5%. Okay. Now the rest of this is very, very similar. We're going to use QDA. Okay, and so I've already done that, but the code is basically identical, so you should look through it for yourself. Okay, and we get a very similar test error and prediction matrix, slightly different. We're going to use logistic regression. Okay, almost basically identical code. Okay, one of the things though now with well, let me say a couple things. The QDA is part of the mass package. But for the logistic regression, I'm using GLM, although there are other commands that are part of other packages, but GLM is just part of the base R package. Okay, so I have my regression equation, and because the outcome variable is either 0 or 1, it's binomial. It's in the binomial family. Okay, but then everything else is the same. Again, we get our confusion matrix here. Then I'm going to perform naive Bayes. So I need to install and load the E1071 package. But again, you go through, you see that it's very similar code. The difference here with the naive Bayes one is that under type, when we're trying to predict, the type is no longer response, but it's class, right? That's indicative of how naive Bayes works. It's classifying these different data points. Also, there is no prob. There's no probability line here, but that's okay. All right. And then finally, k nearest neighbors, and we're meant to use several different values of k. So I used 1, 3, and 10, and I get actually identical confusion matrices with each of these, but you can use different values there. Okay, that is it.